Okay, good morning. It's time to start with our lecture for today. It's 11 o'clock already, so please turn off your computers or your monitor screen and let's get started with the material for this week. Um, Before we get to that, let's talk a little bit about your grades. So I uploaded your grades on Tracks, so I want you to go after the lecture, check your grades, and let me know if you have any questions. I uploaded the scores for the exam and for the homeworks, the ones that we were not there, supposed to be there now, and also for the labs. You will notice that there are some labs that there's no score on Tracks. For those labs, those are the ones that are considered bonus labs. So those are the ones that if you did it and you did it right, are part of your bonus for your first exam. But the other ones, the ones that are listed on Tracks, are part of your homework grade. Okay? So you will see there's lab 2, 4, and 6. Those are posted. Please check your scores and let me know if you have any questions. Lab number 6 was the one in which you were working with the solver and you needed to upload your spreadsheet on Tracks. So I think all of you got 10. So again, please check your grades and let me know if you have any questions. Usually what happens is students wait until the end of the semester, then they start asking about what happened on the first exam or what happened on the first homework. Let's try to answer those questions as soon as possible, so by the end of the semester everyone is on the same page. Okay? So that being said, let's start with the material. So we cover on Thursday we talk about the artificial variables and how to use those artificial variables to solve use the simplex algorithm to solve those problems in which you have constraints which are equalities or greater or equal constraints. And we went through two different methods. The first one is called the N method, and in that one you were using a big number on your first tableau, and you were trying to solve the tableau using those big numbers. By the end, by the optimal solution, you were able to get a solution in which those variables were not part of the solution. The second method is called the two-phase method, and we're going to go over that method one more time because we went through a very simple example, but there's some special cases in which you need to modify your optimal tableau for the first phase in order to transition to the second phase of the tableau. And we talked about that briefly last time, but we want to go talk about that again. And also I have a problem that I want you to work on Teams. So let's see if you can work on that problem. That problem is going to be a bonus for your second exam. So you're going to have to work a little bit on it. But if you get it right, I'll give you 3 points for your second exam as bonus points. Okay? So you're going to go over this, and then I'll let you work on that problem. And then if we still have time, I'm going to start with the lecture number 8 that I uploaded last night. Well, actually this morning. So something happened with Tracks yesterday. I don't know. It was not working, so I was not able to upload the materials. So I needed to do it this morning. So hopefully you were able to get those slides for today. Okay, so the two-phase method, just as a review, eliminate the use of the constant m. And this method solves the LP in two phases. So phase 1 tends to find the starting basic physical solution. And if you find one, then phase 2 is involved to solve the original problem. Okay, so from the first phase, we try to find the starting basic solution. Then we move to the second phase and try to solve the original problem. So in this table, the method is summarized. I make a highlight here. If the minimum value of the sum is positive, the LP problem has no feasible solution. Okay, so keep that in mind. That's one of the special cases. Okay, so on phase 1, if you find that the minimum value of the sum is positive, then the LP has no feasible solution. So let's walk you through these problems. So again, we have three different types of constraints: equalities, greater or equal, and less than or equal. This one is very easy to handle. You have a slack variable, and that can be part of your initial solution. But when you have that slack variable for this constraint, that's a -1, and then for this particular constraint, you cannot add any variable because it's already an equality. So what we do is we add those flags and those variables to our solution, and we put our constraints in equality form. So when we try to solve phase 1, the attempt is to find a starting basic feasible solution for the original problem. So you're going to replace the original function, objective function, regardless of if you are minimizing or maximizing your objective for the original problem. You're going to use a minimization problem with minimizing R. Okay? So R equals the sum of the artificial variables. And solving this minimization problem, this is going to be the objective function for your first phase. Okay, so regardless of the objective function that you had originally. So that's what we do in the first phase. We establish our objective function in terms of your artificial variables. So in this case, you know that you're going to need two, because one for the equality and one for the greater or equal constraint. So you can have an initial basic feasible solution for your first tableau. So this is going to be your starting basic feasible solution. You're going to have R1, R2, and S1, 3, 6, and 4, which are the right-hand side here for the constraint. So the associated tableau for this first phase is this one. So as you see, this is the values for the objective function. Those are negative because you move these R1 and R2 to the left side, so that makes those two negative. So your first row is just those two values. And then you have the constraints coefficients on your second and third row, and fourth row, actually, because we have three constraints. And you have also the values corresponding to the artificial variables for the first constraint and also for the second constraint. And for the third constraint, you only have the value for the slack value. Okay, any questions up to this part? So we changed our objective function to this one. We are minimizing the sum of the artificial variables. What we are trying to do by doing that is we want to find an initial solution for our problem, right? That's our goal in the first phase. But we cannot do that if we don't add those artificial variables, because you will not be able to get this matrix, identity matrix, that basically tells you that you have a basic variables, three basic variables for your initial solution. So we have those artificial variables, and now we have our initial tableau. And now we have a group of variables that we can use as basic variables. So we can start looking for our initial basic feasible solution. Okay, so but before proceeding with the simplex method, the R row must be made consistent with the rest of the tableau. What that means is, if you have R1 and R2 as part of your basic feasible solution, you know that this row 0 value should be 0 for those two values. Okay? Right now, that's not the case. And that would not be the case for your first tableau on the first phase always. So you're going to have to modify these values for those variables that are basic variables. Okay, that's always true. You're going to have to do that every time you start solving the method using the two-phase method. Okay, so we're going to make these two values 0. That's the first thing you're going to do. So R1 and R2 are substituted out in the R row by using the following row operations. So what you're doing is just using for this R1 minus 1, you are using your first constraint row. You are multiplying this row times 1 and summing or adding that row to your first row. That will make this value 0. And that's what this equation is doing. Okay, so you want to make that using the row operation 0. So as I showed you last time, so you were multiplying this row times 1, and you are adding that row to row 0. And the second operation that you're going to have to do is to make this one 0 as well. So you're going to multiply row 2 times 1, and then you're going to add that row to row 0. And this is your new tableau after you make those operations. So what we are doing from here to here is performing those row operations that will make these two numbers minus 1. They're going to make that, those operations are going to make those ones 0. But as you can see, also, the other numbers of the tableau on the first row are affected. So when you perform those operations, you have to perform those operations on the other coefficients as well. So now we have our basic feasible solution. We have our identity matrix here corresponding to R1, R2, and S1. And we also have those values for row 0 equals 0. Okay, so now we have our initial tableau. And now we can move to apply the simplex algorithm to this tableau. So, so this is, again, this is the same tableau from here. So what I'm showing here is just the simplex method. So you're gonna enter the most positive value because you're minimizing, and you find the variable that is gonna leave using the ratio. So the minimum ratio. So that means that you're gonna pivot here, and from there you're gonna get this new tableau, and you perform the same operations until you get to this point, which is the optimal tableau for the first thing. As you can see in this tableau, this is very important. The basic solution here includes x1, x2, and s1. Are those artificial variables? No, because your artificial variables are R1 and R2. So there's no problem here with your basic solution. You are able to find a basic solution in which you don't have any artificial variables. So you have your initial solution for your second phase part of the problem. So you have x1 equals 3 over 5, x2 equals 6 over 5, and x1 equals 1. Yes, sir.
So your RHS, like when you're done, does it have to be 0 or can it be negative?
This, it could be negative. It doesn't have to be 0.
And you can't pop.
Yes. So good question. So at this point, what we want to see is that in our basic feasible solution, there is no artificial variable. So that is satisfied here, and your solution is not positive. So if it is positive, that means that it is unfeasible. Okay, so there's no solution. Okay, so now we have our initial solution. So what we do next is the new row is used to solve the phase 1 of the problem, which yields the following optimal tableau. So we can delete these two columns because the artificial variables are not part of the solution, so they fulfill their duty at this point. You don't need them anymore. So you found your first your feasible solution for your first phase. So now you can have, because the minimum R equals 0, phase 1 produces the basic feasible solution, x1 equals 3 over 5, x2 equals 6, 5, and s1 equals 4. At this point, the artificial variables have completed the mission, and we can eliminate the columns altogether from the tableau and move to phase 2. So when you move to the second phase, you don't need the artificial variables anymore. Okay? So we take those artificial variables out of the Tableau and we keep the columns corresponding to the slack variables and also to your original value. So phase 2, this is how the problem is going to look like. You're going to use the coefficients from the first phase. And using those coefficients, now you're going to go back and get the original objective function. So phase 1 has transformed the original constraint equations in a manner that provides a starting basic feasible solution for your problem. Yes, sir.
Your RHS was negative, but there's a value for it. How can you write your objective function? Not treat.
Say that again.
So in this one is 0, the RHS is a little r 0. Yeah, if that was like a negative number.
Yes.
Check your
Yes, you're going to have to add that part to your objective function. Yeah. So we'll go to the, actually, yeah, that's a good point. If it is negative, since you're transitioning to the second phase, you're not using the same objective function. So that coefficient you don't have to add into the original. So it will keep as a solution. It will keep it as a solution for the first Tableau, but it does not affect the objective function of the second phase. Good question. Okay, so it will not affect this, because what you're going to do here is just use the original objective function for your second phase, but the coefficients for the constraints are the ones corresponding to the ones on your first phase. Okay, so again, we have the starting basic feasible solution. But again, we have the same problem when you start solving the problem using the simplex method. You have a basic solution in which you have the coefficients on the first row equals numbers that are not 0. So you have to make these numbers 0. So again, you perform the operations as we stated for the first phase. So we're going to make those 0. So the initial tableau of phase 2 is given here. So you have your x1 is part of your basic solution, and x2 is part of your basic solution, and x1 is part of your basic solution. So because we are minimizing, E1 must enter the solution. It's the most positive number. So the application of the simplex method will produce the optimal in one iteration. And I'm not showing that, but basically what you do is just follow the steps of the simplex algorithm to obtain your optimal solution. Okay, so this is what we covered or discussed by the end of the last lecture. So I'm going to go over this one more time because you're going to be using this to solve the lab. Okay, so the removal of the artificial variables and their columns at the end of phase 1 can take place only when they are all non-basic. Okay, so when you see your optimal tableau for your phase 1, say this is row 0, so when you look at the first column, this is what we saw for our first phase, the optimal tableau for phase 1. These were our basic variables, so none of them were artificial. So this is the first point here. So if the artificial are non-basic, basically what you're saying is that the artificials are not here on the first column of your optimal tableau for the phase 1. Okay? But if one or more artificial variables are basic, meaning that on your phase 1 optimal solution, you have R1, for instance, then the removal requires the following additional steps. So let's say you are able to get that right-hand side column and the value for r equals 0. You still have r1 in your basic variables. Then at that point, you can select a zero artificial variable to leave the basic solution. So you can say this variable is going to leave the solution and designate its rows as the pivot row. Okay, so you're going to use this row as your pivot. Then the entering variable can be any non-basic and non-artificial variable with a non-zero positive or negative coefficient in the pivot row. And then you have to perform the simplex iteration. So let's say you know that x1 and x2 are part of your basic variables. So let's say we had x3 as well, and we have r1 and s1 e1. At this point, we know that x1 and x2 are basic variables, so you cannot perform this step using x1 and x2, but you can use x3. So you can decide to use x3, and what you're trying to do is take this artificial variable out of the basic variables. And you're trying to do that by substituting one of the non-basic variables that are not artificial, and see if by pivoting and adding that non-basic variable that is not artificial, you can find the optimal solution without having an artificial variable in your tableau. Okay? So that's what we're trying to do here in the first step. So you remove, if let's say you enter x3, so r1 left, x3 enters, and you solve the problem, you get the optimal tableau. R1 is no longer part of your basic variables. So now you can remove the column of the artificial variable from the tableau. If all the zero artificial variables have been removed, you can go to the phase 2. Otherwise, go back to step 1. So you're going to be repeating this process until you are able to get the artificial variable out of the first phase. Okay? So this is something that can happen a lot of times. So that's why I want you to go through this problem. I'm going to help you to solve the problem. But I want you to experience how to do this step by step. I'm going to pass that problem now. You're going to be working on groups of 2. And again, I'm going to be answering your questions. So if you get stuck at a particular point of your solution, just raise your hand and I can go talk to you. So I provided you with the tables and step by step trying to help you follow the rules. Again, this is going to help you understand because it involves a lot of steps. So hopefully this problem will help you understand what's going on. Okay, so you have a maximization problem. Consider the following problem. You have 3 variables, and you have 2 types of constraints. The first constraint is less than or equal. The second constraint is greater or equal, right? So you know that for the first constraint, you're going to need a slack variable. So you add that slack variable, and you can make that first constraint an equality. Then, for the second part, you need to add the surplus variable, and you also need to add the artificial variable, right? Because you have a greater or equal constraint. Okay, so you can name that surplus variable E and your artificial variable R. So that's what I'm asking on the bullet or question 8. Want you to put the problem in equation form, add the necessary artificial variables, and formulate the problem for phase 1. So the main difficulty there may be to add those variables, those surplus, slack, and artificial in the corresponding part or in the corresponding constraint. And also, I want you to give me the right objective function. So for the first phase, you need to modify the objective function. For this case, you only have one artificial variable, so please write down the objective function and the constraint for the first phase. Second, okay? Okay, so far you were able to formulate the problem. So at least what I saw from all of you is you have these first phase formulation. So that's correct. Now you're going to use these constraints to fill your first tableau. And then based on the numbers here on the first row and second row, you will decide which one should be your basic value.
We got you.
Yeah, thing is, when you move to the second phase, you need the coefficients from the first phase. So if you don't have those coefficients, I mean, you use the original objective function, but you need to use the coefficients from the first phase.
Okay, that's what we did. I just tore it out. Is it other wrong?
Well, but I don't see it. Oh, yeah. That's what- Yes. Okay, so even though the problem is a maximization problem, when you get to the first phase, you are using a minimization objective function. So you have to look at the most possible. Okay? It's not until you get to the second phase that you solve as you were maximizing.
We did that, we got 0 from.
Yeah. So now you need to find out one of these conditions.
And once we do this, like we did.
Yeah, so once you get those conditions here, you get your basic variable, then you can move to the second problem.
Okay, so it's fine that everything's 0.
So here's our solution. Yeah, so 0, 0, 0, 0, 0, 0, so.
All right.
We started formulating very simple problems, and then we solved those problems with two variables using the graphical method. Then we moved to something more problems more difficult to formulate, more applied problems. But after that, we started looking at solution methods. So this part of the course is very math oriented. So basically, we have this problem. This is how you solve it. And also, we learn how to use the computer to solve those problems. So far you have seen both the applied material and also the more math-oriented material. So this class is a combination of the two. You cannot only formulate a problem and not solve it. You need to know the math behind the solution. But the math by itself is not that useful if you don't know how to formulate a problem. Okay, so both things are very important. So the simplex method is basically a way to solve these math problems. These math problems are coming from real problems. Okay, so I want you to keep that in mind because we have some objectives by the completion of this course. We should be able to do this, to consider real world problems and determine whether or not linear programming is an appropriate modeling framework. So this kind of relates to something we discussed in class, in which you notice that sometimes linear or continuous variables are not the best way to go. especially if you need to determine the number of units as part of your solution. So if you need to decide whether you need to buy 7 advertisements for these people or 8 for the other people, those type of solutions are integer solutions. So maybe linear programming is not the best way to go for those type of problems. And we're going to discuss how to solve integer programming problems later in this class. The second objective is to develop linear programming models that consider key elements of the real-world problem. So we went through some examples, very applied examples during our math formulation session. Solve the models for the optimal solution. So we know how to solve the problems using the simplex method so far, and we also learn how to solve the problems using the computer, so Excel. And now we're going to move to these objectives. Okay, so now I want you to use try to come up with good answers and good questions for these problems that we have been discussing in class. So we're going to interpret the model solutions, the first solutions to the real world problems. What will happen if you get a solution for this model? You're looking only to the revenue you're going to get, and you're estimating your revenue to be $5 for product A and $10 for product B. But what will happen to the solution if you change those profits? Will that affect your solution? Will you get a different solution? So that's the type of question that you might be able to answer in this part of the sensitivity analysis course. So recognize, analyze, formulate, and solve industrial problems that can deal with linear programming. So far, this is what we have been doing in class: linear algebra, introduction to linear programming, graphical solution, and you can see how all of them are related. Okay, and this is how the objectives are linked to those specifics that we have covered in class so far. So we are entering this part of the objectives at this point. Okay, so the learning objective is to discuss how changes in the LP parameters affect the optimal solution. That's what we call sensitivity analysis. We're going to explain how to use Excel, the steps Excel solver output to answer questions of managerial interest, such as what is the most money a company will be willing to pay for an extra hour of labor, for instance. Okay, so recommended readings for this lecture, you can go to 3.61, 3.62, and 3.63 and 4 from your textbook. Okay, so this material is also covered on those sections of your textbook. Shall move to the next. Okay. So the graphical sensitivity analysis, this is the agenda for today. Graphical sensitivity analysis, right-hand side, objective function. So we're going to look at the sensitivity analysis using 2 methods. The algebraic and the graphical method. And also we're going to focus on 2 areas of the model, the right-hand side and the objective function. Okay, so we're going to see how the objective function, if we change the objective function coefficients, how would that affect your optimal solution? If you change your right-hand side, how would that affect your optimal solution? Okay, so this is what we have done in the past 6 weeks. But the subject matter of this section, in general, in LP, the parameters input data of the model can change within certain limits without causing changes in the optimal solution. So this lecture is going to explain the basic ideas of sensitivity analysis. Okay, so this is an introduction. We're going to stop here. We're going to start from here next time. So we're going to start looking the graphical sensitivity analysis, how we can use the model, the solution, how can we change the coefficients, and answer some questions of managerial interest. Okay, so that's all I have for today. So For Thursday, remember your homework and also remember the lab. There's 3 bonus points. It'll be very good for you to have on the next exam. And if you look for me this afternoon, I'm not going to be able to be in my office. So if you need to see me, please send me an email. We can schedule a meeting for tomorrow. But this afternoon, I'm not going to be in my office. Okay? Any questions? Okay, so I'll see you on Thursday.